Good afternoon. All right, let's get started. Is everyone having a good build? Yeah. Did everyone go to the keynote this morning? Yep. Cool. All right, well, welcome to Delivering Applications at Scale with DocumentDB, Azure's NoSQL document database. It's a very descriptive title, one that fully complies with all of our session naming guidelines, and one that is completely uninspiring and unimaginative. I'm at fault for it, so I can ridicule it, but it is the approved session title. And so for everyone who actually made it here by looking at this in your session book, thank you. What we're really going to talk about today are Spartans, zombies, and building for planet scale. There's nothing more that spices up a build session than a healthy dose of zombies. So today what I want to do is I want to share with some practical applications and some use cases that we've seen with people scaling data and data usage with Azure DocumentDB. Azure DocumentDB is our NoSQL, our fully managed NoSQL database service with Azure. I also want to share some details on this morning in Scott's keynote. He announced a few things relative to DocumentDB, and we're really excited today to share some details on those announcements that were made today. So hold tight. Hopefully today you'll learn some patterns that you can utilize in terms of using DocumentDB and scaling DocumentDB, and I'll also share some details on the announcements that were made today and this morning. Okay, so how many people are familiar with this? A good fair number of people. This is Halo. In particular, this is Halo 5. Halo 5 is the latest edition in Microsoft's quite popular Xbox gaming franchise. Halo 5 Guardians was released in October of last year. The interesting thing about Halo 5 is it introduced a feature, a social gaming feature in the game called Spartan Companies. Spartan Companies allows Halo gamers to find other people and embark on missions and do gaming together in a social way. And when the Halo engineering team was looking for a platform and a solution for building this service, one of the things that the set of problems that they faced were they needed to find a data and data platform solution that would scale to all of the Halo users that are out there today. In addition to that, they were looking for a solution that would give them really good performance and low latency access to data. Because what they wanted to do is to actually expose some of these social gaming features during gameplay. And for those of you who have done some of this online gaming and gaming, you'll know that it's not just the image processing that needs to be responsive and lag-free, but as you're presenting data to gamers and users, you need that to be consistently lag-free and very low latency. And so the Halo team was looking to solve for those types of things. And the other thing is they knew they wanted to iterate fairly rapidly. So they wanted to respond to how people were using the service and add features over time. So to meet the needs of the Spartan Companies feature and services and that capability, they chose Azure DocumentDB. So Halo 5 launched on top of Azure DocumentDB for Spartan Companies. It's being used today by Halo to do that social gaming feature. And so what did this do? What were the results relative to using this capability? So I just want to share some data and what the Halo team was able to achieve by using this. So one of the things, as you'll see on the left-hand side, this is just some of our operations data that we look at on the back end as we're managing the service and running the service and looking day over day, request volume. And you see those spikes that were happening. And so it was important for the Halo team to be able to scale up and scale down capacity based on those spikes and as they encountered those spikes. So if you look at those days and the days that associate with various spikes, the first day is actually a set of testing that happened. And the big spike is actually when Halo 5 launched and the feature launched, and they saw a lot of usage on that day. And then the subsequent spike in January is actually when they did a set of free feature updates in January. So they were able to deliver this feature. They were also able to iterate over it quickly because Azure DocumentDB provides a very set of advanced indexing features. So all of the data that's ingested into DocumentDB is indexed, and therefore you can query over that data. And there's a rich set of query capabilities that are offered. In addition to that, we talked about lag-free performance and lag-free experiences. The query latency was below 2 milliseconds at the 99th percentile. So that's the daily 99th percentile of query latency consistently below 2 milliseconds. And so that allows them to serve up that data during gameplay and be confident that they can deliver those glitch-free and those seamless experiences during gameplay. So one of the things that we hear a lot as Microsoft is, hey, how are you betting on your own new technology? As DocumentDB is a fairly young technology, we brought it into general availability almost exactly a year ago in early April. We've talked about how other services have used DocumentDB. MSN is one that we've talked about in terms of how they deliver personalization on their websites and their verticals that they offer for consumers. And this is just another example how we're betting on our own technology. But I think the interesting thing is that Halo 5 is not the only successful game that's using DocumentDB today. And in fact, they're not the biggest game in terms of usage, in terms of volume that we see on the back end for service requests. How many people are familiar with The Walking Dead? So a few people. The Walking Dead is a fairly popular US-based television show. It was introduced in 2010 and now has, I believe, over 15 million viewers. So it's quite a popular show in the US and in North America. And there's a company called Next Games who develops a game for The Walking Dead, or a game based on The Walking Dead. So for those of you who were in the keynote today, I apologize for the gratuitous repetition, but I'll roll the video and let the Next Games team who built The Walking Dead talk a little about their experience with the service.
We were really proud of the fact that we are actually helping the humankind to learn how to rebel the walkers and stay alive. Azure is a key part in that training. You have to be able to do that 24/7 just to be ready. Walking Dead No Man's Land is based on the AMC TV series. We can actually provide new content after each episode within 24 hours. I pretty much knew that with choosing Azure and Microsoft, I would be guaranteed with better support than I would get from any other cloud providers. We know that there's somebody there looking after us. In Azure, we have, I don't know how many hundreds of servers, but then again, why would I care? It's cloud. The latest addition that we've been starting to use in Azure is DocumentDB, which has really helped us to make our development cycles faster, and that actually enabled us to create a very engaging player versus player experience within the game. Many of the things that we would usually need when we're doing backend are already pre-figured out for us by Microsoft. And we were able to deliver such a high quality, engaging game with stunning graphics, good gameplay, and reliable technology.
Let me just back up for a second. So I think it's a really cool use case for DocumentDB, and this is one of those cases where I think I'll just let some of the results speak for the success that the Next Games team was able to achieve with DocumentDB. So again, we see some of the request volume that we see day over day. At peak, the Walking Dead we saw on the back end roughly 1 billion requests per day, and they were processing 1 billion requests per day. And if you look at those spikes, again, those tend to correspond with either release events or actually events with the Walking Dead series. So in particular, that last large spike is when the season ended, or the first half of the season ended, and then you see it pick up when the season took off again in the new year. And then the spikes early on were corresponding to iOS and Android launches. And so this is another case where a backend had to be built to scale to handle these needs. And as those needs grew over time and resizing the data tier, both in terms of throughput and capacity, And so the next games team was able to do this and also deliver very consistent low latency query access. And so they were able to serve this data into in-game experiences and do that predictably. Over time, we saw their query patterns consistently sitting below 10 milliseconds at the 99th percentile. And so that's a high degree of consistency in terms of when you're serving data into these experiences, and if you want to deliver these lag-free experiences, then this is a great example of a team and an application being able to do that. Next games in the Walking Dead game reached #1 in the App Store, the Apple App Store for free apps. So they had a broad set of reach, or broad reach with that particular game. It was downloaded over 1 million times. So I think if we look at the next games, The Walking Dead, Halo 5, all of these patterns, or these particular gaming patterns, and we're going to spend time on how did they actually achieve this success, how did they build this, and how did they scale to billions of requests a day. But I think what I'd encourage you to do as we go through this talk and as we look behind the scenes at the architecture, I think a lot of these apply to other spaces. So be it online retail, personalized web experiences, media delivery, or whatever your field may be, think about how you may apply these patterns and how these may be relevant to you. They're not just necessarily steeped in the gaming specific scenario, but I think they can be broadly utilized. And I think they all stem from kind of this common pattern and common problem. And at the center of that problem is users. Users are great, we all love users, and as developers we want to gain more users, but more users create more problems. We have problems around how many users are going to show up, how many users are going to show up, and when are they going to show up, what are they going to do when they show up, and what are their expectations relative to the experiences that they want to get out of a system. Increasingly, performance is more important for these applications. They're used to consumer experiences and a set of experiences that they use day to day that are very responsive, lag-free. Similarly, users have high expectations in terms of needs, and so over time they change. And so how do you build a data tier and data platform that you can iterate on and that you can evolve over time, and that will do this for your development team, but at the same time, you don't have to worry about the scalability of the back end. So really, it's about how do we balance the needs of these users while at the same time achieving scale and reliability. So for these games, for Next Games and for Halo, the answer was Azure and DocumentDB. And so I want to spend a little time on why. Why did they choose Azure, and why do they choose DocumentDB? And I think Azure certainly benefits both of these scenarios in the reach that you're able to get and the data center presence that you're able to get by deploying your code into Azure. On the data tier side, the database itself is a low latency data tier. So it is designed to handle writes, and it is designed to serve queries with very low latency. And it does this both through the storage layer in terms of how it's optimized and how it sits on high performance SSD storage, but also how we index data. As data is ingested, as you write JSON data into the database, then we will index all properties of that data such that we can serve queries over that data. And those queries are served through a SQL interface. So if you're used to writing SQL queries, you can write a SQL-based query over DocumentDB. You can do filters, projections, you can do inter-document joins, and you can do array iteration. And so there's a robust set of query capabilities that are offered by the service. And it's done in a schema-agnostic way. So what this means is you don't have to a priori say, this is the schema for my data, or you don't have to say, I'm going to define these materialized views for my applications, or you don't have to say, I want these sets of secondary indexes. And so what this does is it allows you to scale, it allows you to get the performance that you need, and at the same time, you can deliver a rich set of experiences, and you can iterate over those data models relatively quickly. So we know that from DocumentDB perspective, and as we talk to developers, one of the things that's super important is that we deliver a broad set of SDKs and tooling to you to make it very easy to adopt DocumentDB independent of where you are, independent of what platform you're on, what language you're using, or what app stack you're using. So at the wire level, DocumentDB supports a RESTful protocol. That protocol is documented, so anywhere that you have a JSON parser and a web stack, you can talk to DocumentDB, and you can do that through that REST interface. We also offer a set of SDKs and drivers for Python, Node, Java, and .NET. And so if you don't want to talk REST and you want to use one of these language drivers and bind to that, you're able to do that, and we provide supported tools and drivers for doing that. And so really what we've tried to do is, independent of what environment you're in, independent of what operating system you're on, what app stack you're using, that you can use DocumentDB for your needs. At the same time, we also appreciate, and I certainly appreciate that, picking up new things is challenging. There's always a learning curve independent of how much standardization there is in terms of, yes, it's just REST, and yes, it's just JSON. There's always a set of learning new tools, learning new SDKs, and things like that. So today we were really, really excited as we introduced our Mongo protocol support. So what this does is, today if you're using stock Mongo drivers, so how many people have used or are using MongoDB today? So we'll say 25%. So if you're familiar with those drivers and you use those tool chains, what we wanted to have you the ability to do is just take those skills and leverage those existing skills and those existing tools as you interact with a fully managed DocumentDB service. And how do we do this? We decided not to do things where writing a bunch of client SDKs or writing a bunch of drivers that kind of look and smell and feel like drivers from the Apache drivers for MongoDB, but they were different. You'd have to pick them up, you'd have to recompile your code, you'd have to do different things and maintain those libraries separately. Instead, what we decided to do was actually do interop at the protocol level. So DocumentDB actually natively supports the MongoDB wire protocol. And what this means is those stock drivers, those stock Apache drivers, starting with the 2.6 drivers, can communicate with DocumentDB today. And this is something that's in preview today. If you go to the Azure Marketplace, you can sign up for access for that. And we'll be admitting people in for access to get your feedback as we go through the preview for this. So a common question that we get as we talk about success stories with DocumentDB and other Azure services is, increasingly developers just want to say, well, tell me more. How did this particular app actually achieve 1 billion requests per day? How did they scale their data tier? How did they get that reliable, low latency access? And I've read the use case on your marketing site, and it talks at a very high level about how this thing was done, but really I want some details on how I might apply these patterns to my application and how I might be able to achieve the same scale that particular application did. So that's what I want to spend some time on today. I think a lot of us, as we look at this problem, we ask ourselves, well, how would they do that? If I had an app and I had a set of data, the typical pattern is, okay, I have a database, I have an app. I'm kind of a database guy, so I always put like the database at the center of the universe. There's no app tier. Of course, there's no, I don't know where this app tier stuff, it's just a database, center of the universe. So you'll have to forgive my, the liberal use of emphasis on this. But the point being, I have an app, I want to write a bunch of data to a database. So I put all that data into a database. I read that data, I query that data, I operationalize that data. As the scale needs of that application increase, then I just scale up that database. I scale it up and scale it up and scale it up so I can handle all of these applications and all of these clients that are actually talking to that data tier. If I need it to go faster, then maybe I'll put a cache in front of it so I get that low latency read access, and everything should be fine. But what happens when the app requests and all of those patterns explode well beyond what you ever expect for a single database or even a single machine to handle? How do you prepare your application and your architecture for that level of scale? And so this becomes not so simple of a problem. And eventually you scale beyond what a single box could handle. And so you need to start thinking about your performance needs over time and how you're going to meet the needs of an increasing set of users that are showing up on your door. And so for teams like the engineering team at Next Games or teams like the Halo team, they go through a set of evaluations and look at a set of technology that I'm sure many of you either use or look at or evaluate when you're looking at the data tier and how do I deliver a scalable data tier with high performance. And so I just want to talk a little about why some of these tools, and maybe you use these tools exclusively or maybe you use them in combination in these services and technology, but I want to talk a little about why they didn't work in this particular scenario. So for caches are super useful and give great performance characteristics. In this particular case, it wasn't a solution that could be used because of the update frequency that was happening over the data, and there was no locality in those updates. And so there was no data locality that could be cached, and so pretty rapidly a caching solution fell apart. SQL, SQL is a great scalable database, has a lot of great characteristics, but because of both the data volume and throughput volume, this would result in a sharding solution for SQL. So you'd start to have to scale out across multiple SQL instances and start sharding and partitioning and distributing your data across multiple SQL instances. The other thing for the team at Next was that their data was inherently JSON. It was consumed by services and the client-side apps and through their architecture was represented as JSON. So it was almost unnatural to put it into a SQL database, although I will say SQL does support JSON, but as you start to have a sharded architecture, you start to lose some of the relational benefits. And then the other piece being just that rapid iteration. And so not being in, it was very advantageous for the Next team not to be in a schema-first system. SQL being a schema-first system where you have to define schema and then write data. When you live outside of that those schema-first systems, you can write data and that can evolve over time, and the app effectively owns the definition of what the data looks like in the data model. The other piece and the other service that was evaluated was Azure Tables. Azure Tables is a really, really good, scalable, cheap, NoSQL solution. Really good for key value patterns. So if you have data that's a key value lookup, and you need to store it cheaply, and you need to store it at scale, Azure Tables is really good for that. Azure Tables runs on spinning disk. So what that means is at higher percentiles, as you get more request volume, you see more latency at the 95th, 99th percentile. You can see higher latency, you get higher variability, and so you don't get that snappy, predictable performance. It is kind of one of those things where you get what you pay for because Tables is quite cheap for the storage that's offered and the request processing that you get out of it. But it also doesn't give you the ability to query over data through secondary indexes. So if you actually want secondary lookups and secondary indexes, then you have to maintain them yourself. So as the team at Next Games looked at different solutions, this kind of drove them to the solution of using Azure DocumentDB for scaling their data. So I think before I dive into their pattern with DocumentDB and looking at their data model and looking at their partitioning scheme, I'll just do a quick primer on kind of mobile gaming and backends. I promise to go through this relatively quickly. But the meta point here is that, and we heard this yesterday in Satya's demo, is that all of these devices are getting they have tons of power. They can do lots of processing. So things like game engine processing, a lot of that can happen on the client. You don't need necessarily a mobile game backend to do that kind of processing. And the mobile gaming backend is actually used more for gamer interaction, managing leaderboards, managing state across different gamers, and orchestrating things like push notification and purchases. So if we look at a super simplified architecture of the Walking Dead backend, and if the team from Next Games, who might be here, are you guys, yeah, so these guys are cringing the whole time. They're like, I can't believe you guys. So they'll cringe on this one too. This is a super simplified version of the backend, which has basically a bunch of mobile devices that talk to cloud endpoints, and then a service-oriented architecture or microservice architecture that has function-based services that interact with various backends. So queues, storage, push notifications. So if you translate this into Azure terms, we have a set of devices that are talking to Traffic Manager. Traffic Manager can route those to the appropriate data center, and then route those to the appropriate cloud service. And those cloud services do processing over that data and interact with the appropriate backend store. For player data, scores, guild, and social-oriented data, DocumentDB is used as the backend store for that. So there's a set of services there that do a variety of things from in-game purchases, the front end and communication with these devices via SignalR, leaderboard and score service, the social and guild service, and then a set of admin notification, and logging analytics is actually used for a third-party service. So I'm just making sure my machine doesn't go to sleep here, which it did. Oops. Okay, so what I want to do is drill down a little bit on these particular services and how they use Azure DocumentDB, how they store data, how they partition data, how they scale data. So this is an example of some player data that's stored from the Walking Dead game. And you'll see it's got a set of JSON properties, and all of that data is partitioned on ID. So it's a workload where the data itself is naturally partitionable, which means that you can take, and what the Next Games team is doing is they're taking a set of collections. And so if you've worked with DocumentDB today, you'll know that collections can act as partitions. And what they're doing is creating a set of those collections and routing data across them using partition resolvers that are available in the SDKs today. And they use the ID as a composite partition ID so that it can route it to the appropriate partition for both reads and writes. So the first part of that ID is the game, the second part is the data center, and the third part is the player ID. So that helps route it to the right partition. And then there are a set of other properties in that document. You'll see there's a Facebook ID, there's a Game Center ID, there's a score, and all of those are stored to support other access patterns and to allow for retrieval of that data with super low latency. So, and that utilizes that indexing technology. And so if we were to look at the API surface area on top of this data and what types of APIs are offered over this data, there's some basic add player, update player, but then you see a set of get player by ID, get player by anonymous ID, get player by Facebook ID, Game Center ID, Google ID, and so this allows retrieving the data based on those IDs that you have. And it doesn't result in other systems where you may not have this data index, you'd be scanning a large set of data. But by virtue of partitioning the data and indexing the data, you get this really fast retrieval time for these filter queries that you can utilize and model the data appropriately. The other data type that's stored by the backend is what's called a guild. And a guild is, think of this as for the social gaming. Guild is really a denormalized data structure. In SQL, you would probably create lots of tables with guild members and pending guild members and messages and relationships of messages and things like that. By denormalizing this data and putting it into DocDB, what you get is a really efficient retrieval of the guild data. So this is a case where if you think about your rendering patterns and your access patterns for your data, and there's a lot of benefits from denormalizing data because you can just pull that aggregate out of the database. And then embedded in that document are things like members. So you have the existing guild members, and you have pending members, and chat messages. And so you can render that very efficiently in your UI and pull it down to the right experience. The other interesting aspect of this is that you'll notice there's something called current challenge stars and total challenge stars. What this allows the backend to do is that's effectively just a dictionary. It's a set of key values, and the app or the front end gets to decide what it stores in those properties, and the back end has no opinion or enforcement of those. Those are all consumed on the front end. And so what this gives is people who are building the gaming front ends a set of flexibility on how they can build features and add features, and the back end supports those features. OK, so what happens when we scale? What happens when I need more throughput, I need more storage? And so that induces what we call repartitioning or resharding. And so how do you do that? How do you accomplish that? And so this is just a really simplified scenario here. But let's say we had 20 partitions. And we wanted to add another partition because we need more throughput or we need more storage. And so as we add another partition, there is a hashing function that's being used that says, where do reads go and where do writes go? And so the steps that you go for repartition are, first you have to introduce the new partition. You add the new partition to the set, but the hashing function knows nothing about that new partition, so you deploy a new hashing function, and at that time, the app or the back end has to use both of those hashing functions. And it has to use both of those hashing functions because data has to be moved and effectively rebalanced across those partitions. So for 20 partitions, if you added another partition, you have to move 1/20th or 5% of the data. And during the move of that data, your writes will use the new hashing function, so they'll make sure they end up in the new place, but reads have to take advantage of both hashing functions. And then once data movement is complete, then you can move both reads and writes to the new hashing function. And so this allows you to bring on new partitions and scale as the application needs to scale. So this is a really useful and common pattern across both Halo and The Walking Dead as they look at how do I add partitions, how do I scale out my data tier for my application needs. And the powerful thing about this is that the partition resolvers also allow you to customize your partitioning logic. So if you had custom logic that says, OK, this is actually how I want to partition my data. Maybe I want range partitioning, or I have map-based partitioning. You can plug that into the partition resolvers. And in fact, there are some stock partition resolvers. And that will all happen client-side for you. The thing that with these collections and this strategy, have to manage is the addition of those partitions. So super powerful, but it's not for free. And so during the midst of a zombie apocalypse, you can imagine we don't all have time for partition management. So the other thing that Scott talked a little about today was introduction of new scaling options and new pricing options for DocumentDB. So what we're introducing today is something called partition collections. So partition collections allow you to say, I want to take a single collection as a logical container for data. And I just want that thing to scale both in throughput and storage. And I don't want to think about partitions. I don't want to think about this whole hashing scheme. I don't want to think about adding partitions. You guys handle that. And really, the contract between the service and the app is you tell us what is your partition key. So you have to tell us how to distribute your data. So we remember in the Walking Dead case, this was the player ID. And then we use a hashing function to distribute that data. So for other cases, it might be you may have a tenant ID that you decide to hash on, or a location that you decide to hash on. And what that guarantees is that for that for that partition key, will guarantee that all of that data gets co-located inside a transaction domain. So if you wanted to do transactions within that partition key, you can continue to do that. And so you give us a partition key, and you give us a throughput value, and then that will create a collection for you, so you can specify the throughput of that collection. From a storage perspective, storage will just grow as you consume it, so you don't have to tell us anything about storage. We'll manage everything under the covers for you. Along with this, we're introducing a new pricing model. So the existing pricing model will continue to exist. So if you want to use what we call these single partition collections that have the predefined throughput and storage, you can continue to do that. Your apps that you've written today will continue to work. But if you want to opt into partition collections, you're also opting into this new pricing model where storage is billed based on consumption, and that's at 25 cents a gig. So this is for high-performance index storage. We think this is competitive with other cloud services that are out there today, other managed database services. And then for throughput on the pricing side, for under $1 a day, you can do up to 40 million requests per day. So you can get a lot of throughput out of these partition collections, and then your storage consumption will just determine how much you pay from a storage perspective. When you create these collections, so I talked about requiring a partition key and a throughput to assign that collection. So at the top of this slide is just these predefined collections. So this is how you interact with the .NET client today to create collections. You give a collection an ID, which is effectively a name that's guaranteed to be unique. And then you give us an offer type. So in this case, S3 is the highest performance collection option. S3 offers you 2,500 request units per second. What request units are, I'll just do a quick diversion or detour to request units. Think of request units as a normalized throughput unit. Because all requests are not created equal, for instance, if you do a very complex query versus a single point get of a document or a write, those have different implications in terms of how much CPU memory and I/O they induce on the back end. So we have a predictable charging mechanism. So the same request that you do over and over will have the same charge, the same request charge. And then those get normalized to a request unit. And so you provision request units, and then you can scale those up and scale those down. They're not static or set. You can dial it up and dial it down based on the performance needs of your app. So in the second case, you can see here, we have a few changes to how you call create collection or prior to calling create document collection. You specify the partition path. So this is a path within your JSON document that we will look at when it gets written to the back end, and we will route it to the appropriate partition based on how you set your partition key. And then your collection throughput. So here you can see we're specifying 100,000 RUs, and it's well above what a single partition S3 collection can support today. So let's take a look at some of the benefits of using partition collections. Let me jump over to a demo. My machine is waking up. I had to apply updates and reboot prior to the session, so I make no promises. Okay, so this is a really simple app. It's a console app. I call it my zombie reanimator. What this does is it creates a document. So this is just based on a dictionary. You can see here we have GUID, which is ID. We've already created this partition collection. Let me zoom in a little bit. So we've already created this partition collection. This partition collection uses ID as the partition key. And so we'll set the partition key just to a unique GUID, just to have some random distribution of that. But those IDs represent zombies effectively. And then we'll set a location. So what we're doing is randomly generating a location. We have a function that we're calling that is getRandomPoint. I'll show how that's used through the application in a minute, but what that effectively creates is a GeoJSON data point. So that's a valid longitude, latitude. When we were building, anecdote is when we were building this app, the first bug that got logged was don't put zombies in the ocean. And I'm like, why? Zombies are like gremlins? I don't know. But that was because we actually use polygons when we create these locations, so we make sure that we're creating these zombies on land masses versus oceans, things like that. But it'll create a valid GeoJSON location that's on a landmass. And then what we do is we set the reanimation time in minutes to just some random number between 10 and 2 days in minutes to say how long did this zombie take to get reanimated. So what we're going to do now is we're going to take this app, and here you can see we're doing a, let me just scroll down here, upsert document. So what upsert does is basically create it if it doesn't exist, update it if it does exist. So we're just basically, and what this app does is it spins up a whole bunch of threads and tries to push the collection as hard as it can. And if you use DocumentDB today, you'll be used to hitting, or you may be used to, and you're pushing it to the limit, you'll get a 429 response, which is a throttling response, and tell you to back off. So with these partition collections, what we can do is we can run this. So I'm running this in a VM in Azure, just so I get some proximity. Actually, let me show you this first. We have a web front end that's also talking to this zombie database that we're doing reanimation with. We have stats that are tracking. So right now, we don't have any documents that are being created, and it's pretty flat line because we're not running any of these clients. So we'll go into our VMs, and I'm going to launch this zombie generator on my VMs. And so pretty quickly, I'm going to start pushing that collection pretty hard. So I'm well above an S3 collection now. I'm pushing over 20,000 request units per second. I'm doing thousands of writes per second, those document writes. And if you look at that and you extrapolate that out, and if you were to sustain that throughput, that allows you to do, the last note there is the billions of requests monthly that you would be able to do if you were to extrapolate that throughput out and continue to push that throughput. So here you can see we're well over 30,000 request units per second. If we go to and we can see that now our stats start getting updated. So we're pushing that collection pretty hard. That data is getting partitioned across multiple partitions. Lots of documents are getting created. We're already at almost 250,000 documents that we've added to that particular collection. So let's go in and we'll spin up another zombie reanimator on another VM. And this client will also spin up lots and lots of threads and basically saturate CPU and network on this particular machine and push that collection as hard as it can as well. And what we're trying to do is simulate a lot of concurrent users that are pushing the system. So if we go back and we look and we see some step functions there, now we're processing close to 60,000 request units per second. And we could continue to push this thing up into 100,000 requests per second. We're already close to 500,000 or crossing over 500,000 documents created. And so then the interesting thing is, okay, I'm ingesting all of this data. That's all fine and good. But now I actually want to build apps and experiences over this data. So if you go in here, this is, for those who haven't used DocumentDB, this is the query. So I have a select star from C, which is C is our collection. So here you can see I'm bringing back a first page of data. And that's going over a collection, so that's over right now, I think, what did I say, 500,000 documents, and we'll probably be at 1 million anytime soon. And so the other thing I can do is I may want to look at things like, you get to see my cheat sheet here. So let's look for documents with zombies with low reanimation time. So reanimation time below 20. And so what this does is starts returning there. Here you can see the reanimation time here is 13 minutes. So maybe I want to find some zombies near me that have quick reanimation time or ones that are taking longer to do reanimation. The other thing I showed in the app was that we were generating geospatial types. So what that allows me to do is then take those points, and let's zoom out a little bit here. So this is just a map, and it's just polling the database and looking for zombies that are being generated in real time, and we're just rendering that in that map. But the interesting thing we can do is and this is happening across all partitions. So these are queries you'll notice that actually don't have a partition key. And so that query actually gets fanned out across multiple partitions, and you can see was quite responsive. but queries with a partition key will always be more performant. So let's look at another query. Let's say we wanted to apply a polygon. So let's do our zombies from Madagascar query. I have young kids, and there's penguins from Madagascar, I think. I don't know. Okay, so here's Madagascar, and these are zombies getting generated in Madagascar. What we've done there is we've done a within query. Within SQL, we've given it a polygon, and because all of that geospatial data is actually indexed in the database, we can do an efficient query of that data. Okay, let me flip back to slides. So just to recap, a new set of data management and pricing options that are available. So the first is partition collections, which I talked about, and this allows you to scale throughput and storage well beyond single partitions. It also allows you to specify pricing in throughput. So you're charged based on throughput, and storage is based on consumption. The other thing that I didn't show, which we'll be releasing in the coming weeks, is native TTL support. So you can imagine for our scenario there where, let's say we wanted our zombies to expire after a week. I could set a TTL property in that document, and the database will basically expire that data after the elapsed time that you set. You can set that property at a collection level, or you can set that property at a document level. And so that's a really nice pattern if you have logging scenarios where maybe you only want data to stick around for a couple days or a week. You can add a TTL property, and that'll TTL over time, and the data will expire, and that'll free up your storage capacity. The database takes care of that for you without consuming RUs or processing power. It's all done on back-end processing. Okay, so the other thing that we talked about this morning, or that Scott talked about, was global databases. And so one of the kind of unsolved problems is we talked about how these apps get distributed across lots and lots of users. But what's really hard today is actually getting those users to interact over the same data. And replicating your data across, building a multi-region application is super, super hard today. And so one of the things that we look at as we introduce global databases is how do we make it really easy for apps to distribute their data across multiple regions and then build applications against that data such that it can be high performant, it can access the data with low latency, and you get predictable experiences against that data. You know, one of the challenges with multi-region replication is that you get eventual consistency, and it's very hard to program an app and actually consume the data on the other end from a meaningful app experience perspective. So when you have a global zombie apocalypse, it's very hard to build a zombie hunter app that is responsive, and you might want to build it on a device to query that same database that we looked at. And so you would want that data replicated across, you know, more than one of the 20 plus Azure regions that are available today. You want that data closer to your users. So what global databases are replicated multi-region databases. At the database level, you can specify multiple regions for replication. And you're able to access that data for read access from the other regions. So for instance, if we had data replicated from East US to West US, that replication happens asynchronously, but with predictable consistency levels. And so you can define, DocumentDB supports various data consistency levels. For instance, you can get read your write semantics, and I'll show a demo of doing that in a minute with a global database. But this allows you to serve your reads to the region that's closest to you, but writes go to, in this case, writes are going to a single region. So this is an architecture that writes go to a single write region, and then those the replication actually replicates all of those writes to other regions based on defined consistency levels and adhering to defined consistency levels. We also allow you at the application layer to say, I want to cut over with full continuous availability. You can do a cutover of your write region. You can say, I don't, either because of business reasons, because you want to do BCDR, or you may be seeing gray failures in a particular region. You can say, okay, something weird is going on in West US, I'm out, and flip over to East US. And all of your data will be there. And from a client perspective, the nice thing is you don't have to deploy new application bits to do this failover. So here you can see an example of how we instantiate the client. And the client still gets a URI that's global. So that URI is global. You instantiate this client with the highlighted line that says new document client. This is, again, is the .NET SDK. But above that, you'll see we're passing in a set of preferred regions. So you can imagine that in your app config, if you're deploying something based on .NET, that you would specify which region that you're deploying into. And that region would get picked up and pushed in as the preferred region. What the client will then do is we'll try to serve the request out of the preferred region. And so assuming that you've selected that as a replicated region, it will use that for your reads. And then writes will go to the write region. And the client will take care of that to know which is the write region and whether the read region is available or not. So let's take a look at how this might work. Let me switch over to the demo machine. Take down our zombie generator. Okay, so one thing I just wanted to highlight before I showed the demo, what I have is I have an Azure website that's deployed in East US and West US. And then we have a database replicated across East US and West US and currently set with a primary write region. When I deploy my East US website, I give it a preferred region. It's actually East 2, but I give it a preferred region of East 2. And then my West Coast website, I give it a preferred region of West US. And when I do a write, the interesting thing what I'm doing here is I'm actually doing a concurrency check. I'm doing an access condition check here with an E tag. So what this guarantees is that I get read my write semantics. And so even if I'm writing across another region, I get an E tag and I say, this is what I read, this is what I want to update. And now I'm going to give you that E tag. And so you'll get a concurrency violation check if that E tag doesn't match. And so this ensures that you know the data that you're operating over. So let's take a look at this website. So really simple sample website. Database guy, right? Okay. We said that. Okay. So I'm just going to reload these websites. So currently, I just want to show a couple things. So both of those, let's look at the URIs, because those tell you what regions they're in. In the HTTP, in the address bar, you see the top one that says Global DB West. So that website is deployed in the West Coast. On the right-hand side, you see Global DB East. That database is deployed on the East Coast. As I talked about, the preferred regions are different when those websites spin up. On the West Coast, we pass in West Coast. On the East Coast, we pass in East Coast. And you can see the read regions, we actually expand out to there's underlying DNS entries so that you aren't subject to DNS failures and things like that. So the client will cache these things and know the actual DNS entry as well. And so we're spitting those out here just to show which region is actually being communicated with. But so this one, so the West Coast is talking to the West Coast for its reads. The East Coast is talking to the East Coast for its reads. And here you can see write latency differences. So both are getting pretty low latency reads. But the primary write region is actually the West Coast. And so on the right-hand side, you can see the write latency that is almost double, actually more than double, of the West Coast. And so what we can do So this is just running and updating. Let me minimize these. So what we're going to do now is, what did we say? What was the right region? The right region was West US. Okay, so we're going to do a failover. So I talked about how you can do application-driven failovers. So this is talking to the Azure resource provider saying, hey, I want you to reset the primary write region of this database, and we're going to reset it to East US, I believe. Yes, let's reset it to East US. So this is just a really simple app that uses that resource provider interface, and it goes and sets, it's now triggering effectively a manual failover of the write region. And so what happens is that will fail over the writes. We'll make sure that we don't lose any in-flight writes that are happening to the write region. The failover will happen, and if we go back to our apps, it generally takes 5 seconds to do these failovers. Let's see where our apps are. So these guys are taking, let me refresh. So we failed over to East. This is one of those dramatic moments in a demo where you're like, should I have used real code or just lied? Okay, so you can see the East website has failed over. This guy's picked it up. This guy's still loading, still loading, still loading, still loading. So one guy that failed over. Stop this guy. Come on, West Coast. Oh, I should have faked it. It's in preview. Okay, so this guy will reload. I know it will. I know it will. I know you have it in you. But you can see here on the East Coast that this guy's already failed. This guy's already picked up the new configuration. I'm sure all sorts of alerts are going on off back home at the moment. But the West Coast will also fail over. It'll pick up the new write region, and then what you'll see is the reads stay consistently low latency because those reads are still being served through the preferred region, and the West Coast its writes will actually end up with higher latency. You'll see that above 100 millisecond end-to-end write latency on that as it picks up the cross the country write latency. Okay. So that is global databases. And as I mentioned, global databases are available in preview today. You can go to this URI and sign up for global databases. And then you'll get details on how to use it. And we'll be bringing people into the preview over the next month to get your feedback and have you kick the tires and use this new capability for DocumentDB. So just a few more, as we wrap up, a few more resources. To get you started, we talked about different scaling options for collections. If you want to take a picture of something, that might be a good thing to take a picture of. New pricing options, sign up for global databases, access to Mongo protocol support, and then some getting started things. And so before we wrap up, I do want to say a big thank you to the folks at Next Games for letting me probably misrepresent their story in some way, shape, or form, but they've been awesome in terms of giving us access to their designs and their thinking and how they built the service and how they built this very successful game, and also the team at 343, which is the Halo team. So I just want to say thank you for both of those teams for the work we're able to do together. So that's it. Thank you. I don't know how Q&A works, so.